Hey guys, today we're doing Chapter 5, Sections 1 and 2. They're put together because really Section 1 and Section 2 are based on the same thing. We're just talking about our SOHCAHTOA, so I just figured it's all review. Let's just shove them together into one lesson. So, Section 1 is on trig ratios and right triangles. So this is just your normal SOHCAHTOA. If we're given the triangle ABC over here, we want to name the following. So the side opposite of angle B, we would call that lowercase b. Okay, the side opposite of A, we would call that lowercase a, and the side opposite of angle C, we would call that lowercase c. So the sides are always lowercase letters, whereas the angles are capitalized letters. And then what is another name for this side B here? That's called the hypotenuse. So the leg opposite of angle A is leg A, and the leg opposite of C is C. The leg adjacent to angle A would be C, and the leg adjacent to angle C would be A. So this leads us to our SOHCAHTOA. So sine is the leg opposite of A over the hypotenuse, so we say opposite over hypotenuse. The cosine is the leg adjacent to A over the hypotenuse, so that's adjacent over hypotenuse. And the tangent of A is the leg opposite of A over the leg adjacent to A, so that's opposite over adjacent, which is just our SOHCAHTOA. So given this triangle here, we want to find the following ratios. If I want the sine of A, well, angle A is right here, and I'm looking for opposite over hypotenuse for sine. So the opposite is 12, the hypotenuse is 13. This would be 12 over 13. For the cosine of A, I'm looking for adjacent over hypotenuse, so that would be 5 over 13. For the tangent of A, that's opposite over adjacent, so this would be 12 over 5. Sine of C, here's angle C. I want opposite over hypotenuse, that would be 5 over 13. The cosine of C is adjacent over hypotenuse, which is 12 over 13. And the tangent of C is opposite over adjacent, so 5 over 12. If we want to find the measure of A and C in degrees, we can use our inverse sine, inverse cosine, or inverse tangent functions. So let's just say I have the sine of A equals 12 over 13. Well, in order to get rid of the sine here, what I can do is I can apply the inverse sine to this whole thing, and that cancels those out. If I do that to one side, I have to do that to the other, so this becomes the inverse sine of 12 over 13. So then I have A equals the inverse sine of 12 over 13. I can just plug that into my calculator, and I get 67.38 degrees. Okay, and then you can do the same thing with C, so I could do like the inverse sine of 5 over 13. That's going to give me angle C, which is 22.62 degrees. So we have what are called degrees, minutes, and seconds when we're talking about using degrees. Basically, a degree can be split into minutes, which are 1/60th of a degree, and seconds, which are 1/60th of a minute. So it's kind of like a clock or hours in a day. An hour is split into 60 minutes, and a minute is split into 60 seconds. Okay, it's the same type of thing, it's just we're talking about degrees. So, basically, the way that we write it, this is our symbol for degrees, this is our symbol for minutes, and this is our symbol for seconds. If I know that every minute is just 1/60th of a degree, I can rewrite 22 as 22 over 60. And then I know that each one of these is 1/60th of a minute, which is 1/60th of a degree, so 60 times 60 gives me 3,600. So that means that each second is 1 over 3,600 of a degree. So I can rewrite this as 30 over 3,600. And when I do that, that gives me my decimal approximation for degrees. So basically we just want to make sure that we can convert between the decimal approximation and the actual measurement given degrees, minutes, and seconds. Okay, our next problem, we've got a surveying instrument is 4.5 feet above the ground. A surveyor marks a point 50 feet from the base of the cliff and measures the angle of elevation to the top at approximately 61 degrees and 39 minutes. First thing we want to do is draw a picture to represent the situation. So I've got my surveying instrument here. I'm not a very good drawer, but you know. And that is 4.5 feet above the ground. Okay. And a surveyor marks a point 50 feet away from the base of a cliff. So here's my cliff, and this distance here is 50 feet. Okay, and he measures the angle of elevation to the top at approximately 61 degrees, 39 minutes. So that would be my angle of elevation, where this distance is 4.5 feet. Alright, so I've got my picture here. Now I can solve my problem using the fact that this is a right triangle. So I know that I have my opposite and my adjacent side to this angle here. That's opposite over adjacent is tangent. So I can say the tangent of 61 degrees and 39 minutes is equal to x over 50. Now 61 degrees 39 minutes, I need to be able to write that as a decimal. So if I take that and rewrite it as 61 plus 39 over 60, that gives me 61.6. So now I have the tangent of 61.6 equals x over 50. I'm going to multiply both sides by 50 to cancel that out. So then in my calculator, make sure you're in degree mode, and you're going to plug in 50 times the tangent of 61.6, and you should get 92.47. So once the total height of the cliff, that's this height here. We also need to add in the height of the surveying instrument, so I'm going to add 4.5 in. And that gives me a total of 96.97 feet. So that's going to be my overall height of my cliff. Alright, that's everything for section 1. Section 2 is on the law of cosines. So section 1 is just kind of an overall review of our right triangle trig, SOHCAHTOA. It's what happens when you have right triangles. But section 2, we start talking about what happens when you don't have a right triangle. So the law of sine, or the law of cosines, is something that we can use when we don't have a right triangle. There's no right angle. This is true for any triangle ABC, where A is the length of the side opposite angle A, B is the length of the side opposite angle B, and C is the length of the side opposite angle C. Okay, so we've got this triangle here. These are our 3 different possibilities for our law of cosines. Now you'll notice that they're the same exact thing. The only thing that's changing in each of these is that this, whatever angle it is here for your cosine, has to be the angle on the opposite side of your equal sign. These they don't matter where they are, so you can flip those around, it doesn't matter. But these, C and C, B and B, A and A, those have to be where they are in these equations. So the first thing we want to do is draw a picture. So I'm just going to draw my parallelogram here. I know that this is my acute angle, so I'll label that 70, and I'll just say that this side is 10 and this side is 15. Okay, so what is the length of the longer diagonal and the shorter diagonal? Well, if I draw on a diagonal here, I know that this diagonal has to be the shorter diagonal because this angle is going to be acute, whereas this diagonal, this angle is obtuse, so I know that this side length has to be longer than this side length. So, to figure out my longer diagonal, that's this one, I've got my 10, 15 here. This is a 70-degree angle, which means that this has to be 110 degrees. So I've got my 110-degree angle, this is 10, this is 15, and I'm looking for this side here. So I'm going to use my law of cosines. I'm going to say x squared equals 15 squared plus 10 squared minus 2 times 15 times 10 times the cosine of 110 degrees. Okay. So then 15 squared plus 10 squared gives me 325. 2 times 15 times 10 gives me 300. So if I take 300 times the cosine of 110, that gives me like negative 102.6, and then I'm going to take 325 minus that answer, and I get x squared equals 427.6. Then I take the square root of that answer, and I get 20.68. So this diagonal here is 20.68, and that's the longer one. Now to find my other diagonal, the shorter diagonal, I have the same picture, but this time I'm using my 70-degree angle instead. So I've got x squared equals 15 squared plus 10 squared minus 2 times 15 times 10 times the cosine of 70. So this, of course, is still 325. This is still 300, but now I have the cosine of 70. So if I take 325 minus 300 times the cosine of 70, I get 222.39. Then I take the square root of that, and I get 14.91. And that's my shorter diagonal. Alright, so I found the longer diagonal and the shorter diagonal, and I was able to do it all just using the law of cosines. That is everything for sections 1 and 2.